1 light year is 9.4 trillion kilometers. That distance alone is enough to make every piece of technology we have ever built look completely ridiculous. No spacecraft currently in existence could cover that distance within a human lifetime. For comparison, Voyager 1 has been traveling since 1977, almost 50 years, non-stop at around 17 kilometers per second, faster than almost anything humans have ever built. And yet, the probe is currently about 165 astronomical units away from the Sun, just under 25 billion kilometers. Measured in terms of light travel time, Voyager 1 is a mere 23 hours away from us. It won't be until a few years from now, likely in 2029, that it crosses the threshold of a full light day. The distance light travels in 24 hours. A light day after nearly 5 decades of flight, traveling at one of the highest speeds ever achieved. However, one of the most difficult parts of a long journey is actually the start. To overcome Earth's gravity, leave its gravitational field entirely, and head out into open space, a rocket must reach what is known as escape velocity, about 11 kilometers. That is faster than a bullet travels. But even once that is achieved, you are far from being out there. The first few million km within the solar system feel like a real slog for a spacecraft because the Sun's gravity pulls on everything nearby. It took the Voyager probes decades just to get past the outer planets. And where does our solar system actually end? Not at Pluto. That is a common misconception. The Sun's sphere of influence, the heliosphere, extends much further, reaching out about 120 astronomical units before the solar wind is halted by the interstellar medium. Beyond that lies the Oort cloud, a region of icy objects that likely stretches for a full light year. The real problem with such a journey isn't the distance itself. It's what lies in between, namely, almost nothing. Imagine flying for years while the view outside remains virtually unchanged. No planets on the horizon, no landscapes, no events, just stars shifting almost imperceptibly over the course of decades. The space between stars is so empty that an average cubic meter contains less than a single atom. Even within a solar system, it takes years to pass anything that looks like a potential next destination. But once you are truly traveling between the stars, we are no longer talking about years without highlights, but centuries. Entire generations could be born and die on board without the view outside changing significantly. Let's consider 3 real-world speeds and see what a light year would mean for them. Let's look at Voyager 1 again. Traveling at around 17 kilometers per second, it is the fastest human-made object ever to leave the solar system. Yet it would still take about 17,000 years to cover a single light year, roughly the span of time from the first cave paintings to the present day, just for 1 light year. The Parker Solar Probe is significantly faster. During its extremely close flybys of the Sun, it has reached peak speeds of nearly 700 kilometers per second. Even at this record-breaking pace, the journey across a single light year would still take around 430 years. Then there is Breakthrough Starshot, a concept, not yet a reality. The idea involves tiny probes powered by lasers accelerated to about 20% of the speed of light. At that speed, traversing a light year would take about 5 years. What stands out is that while higher speeds dramatically change the numbers, they don't automatically solve the problem. At 20% of the speed of light, we are talking about masses in the gram range, not a spacecraft carrying humans. As soon as you factor in mass, life support, and the need to slow down, the realistic speed immediately drops back to a fraction of that figure. Another issue is energy requirements. Accelerating a crude capsule to even a fraction of the speed of light exceeds the capabilities of current propulsion systems by several orders of magnitude. Chemical rockets are fundamentally unsuited for this task. Even ion thrusters, which are highly efficient, take an enormous amount of time to build up any significant speed. Then there is the issue of radiation. In interstellar space, there is no protection from a planetary magnetic field. Cosmic radiation would bombard any biological tissue over the course of years, and as yet there is no practical shielding capable of reliably preventing this over such extended periods. Dust presents another almost absurd problem. At extremely high speeds, even a tiny speck of dust becomes a projectile with enormous impact energy. And even if a spacecraft survives all this, communication becomes a challenge in its own right. Even from the edge of the solar system, a radio signal takes hours to reach Earth. At a distance of 1 light-year, it would by definition take at least a year for a single one-way message to arrive. A conversation as we know it would simply no longer be possible. The stars are so distant that their positions shift only imperceptibly even after a journey of a full light-year. The familiar constellations would remain recognizable, virtually unchanged for vast stretches of the voyage. Only upon truly approaching a target star would it grow steadily, brighter, eventually outshining all the others. The sun, by contrast, would slowly fade. It would not vanish abruptly, but grow dimmer over months and years, eventually becoming just one point among many, scarcely distinguishable from the other stars. You wouldn't notice the speed itself either. Without acceleration, movement through space feels no different from standing still. You would only be able to detect it, if at all, by the slow shifting of the view outside. No rushing sound, no jolting, no physical sensation of speed. Just that almost imperceptible, very gradual shift of the stars observed over the course of years. Proxima Centauri, the star closest to us, is about 4.2 light-years away. So after covering a single light-year, you wouldn't even have made it a quarter of the way to our nearest neighbor. And Proxima Centauri is actually the lucky case here. Most stars visible in the night sky are 10, 50, or even 100 light-years away. A single light-year doesn't even get you close to a real destination. And even that 1 light-year probably wouldn't take you entirely out of our own system. The outer edge of the Oort cloud is estimated to be up to a light-year away. Some estimates go even further, up to 2 light-years. Theoretically, you could travel a full light-year and, technically speaking, still be within the sphere of influence of our own sun. This shifts one's perspective quite dramatically. What sounds like a colossal distance is, on a cosmic scale, little more than a first step. The Milky Way has a diameter of over 100,000 light-years, and even within our own little corner of it, the so-called Orion Arm, there are thousands of stars, each one further away than a single light-year could possibly cover. In that context, a light-year is practically negligible. It is not a figure that carries any weight on a galactic scale. A single light-year is more than enough to push any current technology to its limits regarding energy, time, and what the human body can endure over such vast periods. Yet, compared to the rest of the universe, that very distance is practically nothing. This becomes especially apparent when you compare the figures. Voyager 1 would take around 17,000 years. A theoretical project like Breakthrough Starshot, if it ever works, might manage it in about 5 years, though only for an object the size of a postage stamp, not a spacecraft carrying humans. The entire history of space exploration, from the earliest probes to the boldest concepts currently in existence, essentially spans the gap between these two extremes. And even at the upper end of that scale, traveling at 20% of the speed of light, you still wouldn't technically have fully escaped the influence of our own sun after covering a distance of 1 light-year. Everyone knows, of course, that the universe is vast, but the fact that even the very first, smallest step into that vastness is currently practically beyond our reach is truly staggering. I hope you enjoyed the video, and I'll see you next time.